So this is not exactly part of the topic of this school, which is integrability, but there is overlap. And hopefully we will reach that in my talk tomorrow and in Kolya Gomov's talk on Saturday. Maybe the two things will combine. That's our hope. I can promise that Kolya will do it because he's not here. So let me give you some references. My lectures will follow mostly this review of Marinho lecture notes. They're much more detailed than what I'll be able to give here in 4 hours, so you can look at them for some more details. I will try to stick with the notation there in some places. I will change it. And he is quite meticulous, so there aren't many typos in these notes. The original calculation of the localization in 3 dimensions was done in this paper of Kapustin, Willett, and Yakov, and there were 3 more versions of it. So this is localization. This is review. So the first paper did it for theories with n equals 4 supersymmetry, which actually for the most part is what I will do, but I will use the notations from this paper. So actually these 2 papers have n equal 2 SUSY, and in my paper, much more recent, it's also n equal 2 SUSY, and it's also some funky observable that I will not talk about. But here, the localization uses, in addition to spectral analysis to do the calculation of the one-loop determinant, so we'll get there at some point, it uses an index theorem. So actually I will not use it in this talk. I will use a more pedestrian approach of the spectral analysis, but if you want that, it is here. Then the applications of this to ABJM theory are in this. So this is solving the ABJM matrix model. In 3 different ways. So this is in the large N, so all lambda, the 't Hooft coupling, a perturbative in 1 over n. This is a much more general solution that is valid only large N, large lambda. And this one is a large lambda, exactly. So 3 different approximations. Of course, they give the same answer where they in overlap regimes of validity. And this is what I'll talk about next week during my seminar on Thursday. So this is a gravity calculation. So for the most part, today I will follow this paper or this paper, and so this is today, and tomorrow it will be this. So this is a school about integrability, which is where you learn to calculate all kinds of quantities exactly in integrable models, mostly in the T. So we mainly focus here on n equals 4 super integrals in 4D or ABJM n equals 6 different assignments. In 3D, and integrability usually you usually start with calculating anomalous dimensions of local operators. There are generalizations of this, but very crudely it's stated like that. And in particular, what you calculate is something divergent. So if you were going to do Feynman diagrams, you would find what the quantity that you're calculating is a coefficient of some divergence, polarizing divergent graphs. In localization, we actually usually calculate finite quantities. Of course, the anomalous dimension at the end is a finite quantity. So we calculate finite quantities, which is the expectation value of BPS protected observable. And so we need to look at supersymmetric theories to find BPS protected observables, and we have a very restricted class of observables that will preserve supersymmetry. So while here we try to calculate the spectrum of all operators in the theory, here we will look only at BPS observables. So it's a smaller class of observables, but on the other hand, there are some benefits. So we have less observable. We have more theories. So it's enough to have n equal 2 in 3D or in 4D, n equal 2 also in 4D, or in some cases n equals 1, and so on. You can also study it in 2 dimensions and then 5 dimensions. And it's also more exact. All order in 1 over n and lambda. So less observables, and here's only. So there are many quantities you may want to calculate. As I said, not so many, but the typical ones are the partition function on a sphere, say S3, on S4, a half BPS Wilson loop on the same space, or it's the same as a circular Wilson loop in the plane. You can calculate the index, which is the same as the partition function, as the partition function. On S2 plus S1, S3 plus S1. So if you have a circle, you can calculate the thermal partition function, but in this case, what we are calculating is not a thermal partition function, but a supersymmetric one. So you use a supersymmetry preserving boundary conditions along this S1. You could calculate other kinds of observables like surface operators. So that's two-dimensional observables, say in 4 dimensions. It wasn't calculated in 3 dimensions, but in 4 dimensions it was calculated. So it's a co-dimension 2 defects. You can, in 4D, you can also calculate the half loops. You can calculate hemisphere partition functions. This was done in 2D, domain wall. And I'm essentially running out of the list. There are a few other refinements of this, but this is more or less it. So this is a general overview of what can be done, but in my talk I will focus on a 3D smoothing theories on S3. So today it will be more general. Say n greater than 2, n equals 3 or 4 will be fine. Most of what I say will be true also for n equals 2, but simplify it a bit. And tomorrow it will be ABJM. So we consider the theory on S3, and the trick of localization is that we are able to use supersymmetry to freeze out all the modes, or integrate out all the modes of the fields, and reduce the field theory to a zero-dimensional matrix model. So a finite dimensional integral. Then, so this is the first thing I will show you, how to get a finite dimensional integral out of a supersymmetric field theory calculation. But this matrix model, this finite dimensional integral, can be very, very complicated. In many examples we don't know how to solve it exactly, but in the case of ABJM, we can solve it exactly. So I'll show you how to solve ABJM. Matrix model, as I said, there are several different versions of how this can be done at different levels of approximation. And then, if I have some time, I will also discuss and compare the solution to the ADS dual of ADJM, which is M theory on ADS4 cross S7 ZK. So, any questions before I start? So we will be looking at 3D theories. With n equals to SUSY or more. So for those who are not familiar with 3D supersymmetric theories, this is essentially the same as n equals 1 in 4D, and we will use the same multiplets as in n equals 1 SUSY in 4D. We are going to work in Euclidean space, which means there are some complications because the spinners are slightly different and it's hard to impose reality conditions. So psi and bar are independent. And then we use all kinds of conventions for multiplication of spinners. I will stick with the conventions in my use notes instead of writing them down. So things like this. When I write psi bar lambda, I mean psi bar alpha, C alpha beta, lambda beta, and C alpha beta, 0 minus 0. And then I also have a choice of gamma matrices, and so on. So the standard multiplets that we have are vector multiplet and a chiral multiplet. The vector multiplet has a gauge field NU, that's a 3-component vector. Of course, I said that this is the same as the n equals 1 in 4D, where the vector has 4 components. So the fourth component, if you want the component of the gauge field in 4 dimensions around the circle when you compactify it, is sigma. So that's a real scalar field. Then we have the fermion, lambda bar, and the auxiliary field D. The supersymmetry variations are written here. So here we have epsilon and epsilon bar are two independent spinners. So we have supersymmetries generated by epsilon and supersymmetries generated by epsilon bar. If I ever write delta epsilon, then you just need to keep the terms proportional to epsilon on the right-hand side. If I write delta epsilon bar, you keep the terms proportional to epsilon bar. And what is really important in this whole story, which is different from what you are used to, usually the way somebody would present a supersymmetric theory for you would be they would write down the Lagrangian, and then they will write down what are the supersymmetry variations. Here actually, I first write down what are the supersymmetry variations, then I will try to find a Lagrangian that is invariant under it. Of course, this if I do not find a Lagrangian that is invariant under this, then this is useless. But a lot of what I say would be valid for any Lagrangian that is invariant under these supersymmetries. So that's why I don't want to start with a particular Lagrangian and write down the supersymmetry variations. There is another very important thing, and that is that we want these supersymmetry variations to close off shell. So if you calculate a quantity like delta epsilon bar of sigma, we will want this to be equal to 0 off shell. This will not lead to the equations of motion. Actually, this will not be exactly right. So it can be up to symmetries and gauge symmetries. So we want it to be a symmetry or a gauge symmetry, which is not crucial because we will require these symmetries to be preserved and gauge symmetry to be preserved. But we don't, that without imposing the equations of motion, because the calculation that we are going to do is off shell, we want to do the full path integral, not just the classical calculation, so we're not allowed to impose the equations of motion. So this is very important in this whole localization game. This is what we normally do. So you actually need to check this kind of double transformation, and for the most part it works, but then if you calculate delta epsilon bar, the commutator of these two, acting on D, what you get is I epsilon bar gamma u epsilon d plus I lambda comma d plus 2 rho d epsilon times d plus 1/3 sigma epsilon bar gamma u epsilon minus epsilon gamma bar by d. And lambda, this lambda is equal to epsilon bar gamma u. Epsilon times mu plus sigma epsilon bar epsilon. So this term, these two terms together, you can view them as a covariant derivative of d in this direction, epsilon bar gamma mu epsilon. So if I choose a particular epsilon, an epsilon bar, this will define some vector field on S3, and this will be a covariant derivative in that direction. So this would be one of these symmetries. I will demand that the vacuum or any observable that I will calculate will be invariant under translations in the directions defined by this vector field. These terms are a little bit more problematic, and there is no you need this term to vanish, for example, and then you also need some justification for this term. And to get this term to vanish, you can impose a property that d mu epsilon is equal to I over 2r gamma mu epsilon, and the same for epsilon bar, where r is the radius of S3. So far actually I made no conditions on what these epsilons are, but in order for this to close, you need to satisfy a condition like this, which is also known as the killing spinor equation. So there's going to be a finite number of solutions to these equations, actually 2, and these are going to generate the supersymmetries that are valid on S3. Sorry. So, I mean, everything that I do here is slightly different from regular supersymmetry in flat space. In particular, this covariant derivative of epsilon will have a spin connection and so on. So these will be non-trivial spinners. This is similar to what you have in, if you study conformal field theories in flat space, then you know that you have symmetries generated by constant spinners, the usual Poincare supersymmetries, and you're going to have spinners, supersymmetry parameters that are linear in space, and they solve an equation of this form. So in flat space, either epsilon is equal to epsilon naught, constant, or epsilon is equal to x mu epsilon naught. So these are the usual Gibbon spinners, the usual Poincare supersymmetries, and these are the superconformal supersymmetries, conformal supersymmetries. So that's these are our supersymmetries. Any questions? So I said we're going to stick with these supersymmetries and try to find Lagrangians that are invariant under them, but of course the direction we're going is ABJM, so it's going to be really bad if ABJM would not work, and in particular the vector part of ABJM is Chern-Simons. And some of them supersymmetrize it. So S super Chern-Simons is equal to minus integral v3x trace epsilon mu rho. We have an epsilon tensor in 3 dimensions. minus lambda bar lambda plus 2 sigma. So hopefully people are familiar with the Chern-Simons action. The supersymmetry, of course, we need to include all the other fields in our multiplet, sigma, lambda, lambda bar, and d. They appear in this very simple way. So actually, you can just integrate them out, and you're going to end up with a regular Chern-Simons. So this is equivalent to a bosonic Chern-Simons. But this equivalence will break down when we add matter fields, when we complicate the theory. So then these fields will couple to the other fields that we will add, and it will no longer be equivalent to a bosonic theory. But here you can just integrate them out here linearly. So that is very simple. So I wrote down the supersymmetry variation. So as a homework assignment, you can check that this is invariant under supersymmetry. If Collier's talk is boring, you can do that. But that's unlikely. Now, here I did not include a coupling constant, which usually appears in front of the action. So, in the path integral, the partition function is going to be equal to integral A, and so on, all the other fields, and then e to the ik 4 pi s super Chern-Simons. So the coupling constant of Chern-Simons is k, and it is quantized. So k is an integer. Otherwise, this action is not gauge invariant. So this is not gauge invariant. Under gauge transformations, you can get a kind of overall term, and if to make it gauge invariant, you consider it a 4-ball where the 3 sphere is on its boundary, and then you discover that under gauge transformation it changes by 4 pi times an arbitrary number. So if we quantize it, or 8 pi squared times an arbitrary number, so if we multiply it by an integer times an integer, 8 pi squared times an integer, if we multiply it by this, what we will get is an integer times 2 pi, and 2 pi e to the 2 pi I integer, of course, is 1, so then it will be gauge invariant. In AHAM, we then define lambda of coupling over k, so we have the 2 parameters, and lambda, which we later will want to expand. Now you can try to write other actions for the vector multiplets, and the standard actions you can add are a Young-Mills, super Young-Mills, I'll come back to that later, and also you can add a Fayet-Diopoulos term for any abelian gauge group, for any U1 factor, and an F5 factor. So these all these you can add to this So this is what happens if we have just vector fields. But as I said, we will also want to add matter fields, and the matter fields will be the n equals 1 chiral multiplet in 4 dimensions. And they will include a scalars phi and phi bar, scalars psi and psi bar, and a auxiliary fields F and F bar, and their supersymmetry. So now comes the issue of how much supersymmetry we have, because, well, you know, in 3 dimensions, a scalar field, if we write an action term in the Lagrangian of this form, and this will be dimension 3, then the dimension of phi will be 1/2. But this dimension can get quantum corrections. And indeed, if you have n equal to SUSY, then delta doesn't have to remain 1/2. If you have n greater or equal to 3 SUSY, then the dimension will remain 1/2. So delta classical of phi is equal 1/2, but if you just had n equal to supersymmetry, there could be an anomalous dimension. Yes.
How fields from vector multiplet can appear transformations of the kernel?
So this is when the field is charged, when the chiral multiplet is uncharged, then these the vector fields will not appear here. This only appears when these vector fields are in some when these chiral fields are in some representations of the gauge group, and then this will appear. Yes. So if this is uncharged, if I don't have a vector multiplet, just put this sigma to 0. So you should think of this sigma. So I have this I epsilon sigma phi term there. So you should think of this as sigma is a field in the vector. So you should think of this as, if phi is in a representation R, I need to take the representation of a sigma, this acting on this field phi. In particular, if it's a neutral field, these terms, this will be equal to 0. This will not appear. So all these terms will go away for uncharged scalars, or chiral fields, but then these you should also just be able to integrate them out. They will have no effect. So what we're interested in is the coupling of the chiral fields to the vector fields. So in this, this is a little bit of sloppy notation where you should think of the sigma as a matrix and phi and psi as vectors. And then you use a vector multiplication, matrix multiplication. But you can do it for general representations. Thanks for the question.
Can we get this formula from some sypersymmetric formulation?
Yes.
And how is it simple or not?
sure. I actually haven't worked it out in superfield notations, but you can use the same superfields you use in 4 dimensions. So if you like if you like superfields in 4 dimensions, I think it's essentially the same.
What is the second super charge? Well, the second transformation have n equals 2, so maybe have one more?
Well, we have epsilon and epsilon bar.
So.
Yes, and we have, and as I said, so actually it's essentially 4 transformations, but this is because of this doubling of the parameters in Euclidean space. I had somewhere the killing spinner equations. There are 2 solutions to them. So these are the 2 transformations. So when I write here epsilon, there are 2 possible epsilons that I can put in all these equations, 2 inequivalent epsilons that I can use to transform my fields. This is actually a point, it's a very good question, because this is a point that is very obscure in all the literature. People write just delta epsilon and don't specify what this epsilon is. And later I will say, okay, now I chose an epsilon, and I work with this epsilon, and I will just call it epsilon again. So at this stage, epsilon is any solution to this equation. Very soon, epsilon will be something very particular. I will choose one of the supersymmetries. Any other questions? So, the issue is that these formulas get complicated if delta is not equal to 1/2. So you see the I/3 there would be multiplied by 2 delta if my fields had a different dimension. And these variations of the auxiliary fields would also get an extra term with a delta in it. So these last terms. So all the formulas I'm going to say from now on exist for arbitrary delta, but I will omit the delta. I will set delta equals to 1/2. It simplifies some of the formulas. The end result is actually much simpler for these theories with more supersymmetries. So I will focus on them, but we can do everything for n equal 2 supersymmetry as was done by Jaffari's and by Hamahosomichi and Lee. And actually, part of the important thing about this S3 partition function, so a question people often ask is, what does it mean to calculate an S3 partition function? You know what a thermal partition function is, but what is a sphere partition function? And actually, what was realized by Jaffari's, or conjectured by him, but turns out to be correct, is that if I look at this S3 partition function for a theory with n equal 2 supersymmetry, and I calculate it as a function of delta, of the dimension. Now I don't know what the dimension is because it gets quantum corrections, but I can just do it naively and just take delta and calculate it. Then the correct value of delta will extremise this S3 partition function. So this is a way of calculating what is the correct value of what is the anomalous dimension of these scale fields. But this is not the direction my talks are going. I'm heading towards ABJM, which is certainly has enough supersymmetry and there is no anomalous dimension. So again, you need to check that the supersymmetry closes And again, you find that if you satisfy this killing spinner equation, everything works. Okay, any questions so far? Yes.
You first write down these transformations, then say, I want to look for a Lagrangian which satisfies this.
Yes.
But what's your guiding principle of writing down the whole set at the first place?
So, well, if you can find another set, then that would be good. But I mean, as I said, in reality, what you do is you start with a Lagrangian that you know. But actually, the Lagrangians you know are in flat space. So you start with a Lagrangian in flat space. If your theory is conformal, you have a canonical way of writing it as on a sphere, because the sphere is a conformal to flat space. So then you have a way of writing your Lagrangian on the sphere. If you know what your supersymmetries and conformal supersymmetries are in flat space, then you can immediately write it on the sphere as well. And then all the Lagrangian, all the conformal supersymmetric Lagrangians you have in flat space will also apply in curved space. In reality, what people do is more complicated, because on this sphere you can also consider massive theories. You don't need to consider only conformal theories. But what these theories are, then, they are not equivalent. When they're massive, they're not equivalent to a theory on flat space. So what you need to do is find a way to define a theory on a sphere, which is which is not conformal. So this addition of these dimensions here, these are not canonical dimensions. So now transformations would be anomalous. So the inclusion of a dimension of delta not equal to a half in these formulas was an extension beyond what was known for the supersymmetry transformations in flat space. So these transformations are a generalization of the usual. So if you take delta equals a half, these would be the usual conformal transformations of the supersymmetries in flat space, or they're actually identical to the supersymmetry transformation in flat space. These new terms are valid only on the sphere, and they allow you to have delta not equals to a half. In 4 dimensions, you can do the same and add an explicit mass term, for example. And then, if you can get this to close, you can also usually write down a Lagrangian with a mass term. But then you need to specify what is your how you couple your fields to the scalar curvature of the sphere, and how to write down the mass terms and so on. So you do both things in parallel. But this is certainly a generalization of for conformal theory it's not important, but for massive theories or anomalous theories, it is a generalization of what you know from usual flat space supersymmetry. Did this answer your question? Any other questions? So I think this is a good time to take a break, and we continue with localization for the next hour.